Hello, we are in Chapter 6, Section 6.5, Solving Quadratic Inequalities. In this video, we are going to learn about the graphing method of solving inequalities. We will start with a simple linear inequality and perceive each side of that inequality as a function of x. Now we will graph both of those functions on one coordinate chart and acknowledge that f of x and g of x are simply the y-coordinates of the points on each graph. So what we're trying to find is where those y-coordinates of the blue graph are more than the y-coordinates of the green graph. In other words, vertically speaking, where is the blue graph above the green graph? And the first thing we need to acknowledge is that at the point of intersection of those two lines, those two graphs, that relationship between those two graphs changes. So let's first find the intersection points coordinates to know exactly where that change occurs. We will do it by solving the corresponding equation and acknowledging that only the x-coordinate matters because our inequality is in terms of x and our solution set will also have to be in terms of x. So as you can see that x-coordinate is 4/3 and we highlight our intersection point first to acknowledge which part of the blue line is above the green line. Since we only care about the x-coordinates of the points where that happens at the end, let's also highlight that part of the x-axis starting at 4/3 and moving right to positive infinity. And that gives us the first view on the solution set for our inequality, the x-interval from 4/3, not including that endpoint, up to positive infinity. Now, this method requires us to be able to draw both graphs of both sides of our inequality, find all the points of intersection between the two graphs, and then visually inspecting on which x-intervals the proper relationship between those two graphs happens. In our case, once again, it was where the blue graph was above the green graph. It works, but in general, it's not really convenient because it requires the view of all the features of the graph that we need to look for, both horizontally and vertically. We are going to approach it from a little different perspective, still looking at two sides of an inequality and graphing them, but first transforming our inequality by isolating a zero on one of the sides, let's say on the right-hand side. This inequality is equivalent to the one we had originally, so it will have exactly the same solution set. Now, we are going back to our original method, but for this new adjusted inequality. So the blue graph is now f of x equals 3x minus 4, and the green graph is g of x equals 0. In other words, y equals 0, which is simply the x-axis. So looking where the blue graph is above the green graph is really looking where the blue graph is above the x-axis. And to identify the points where that relationship changes is to find the x-intercepts of the blue graph. That means solving the left-hand side of the inequality equals 0. Just a single equation with 0 already isolated. Much easier than what we had to do in the first attempt. Also, we don't really care about the y-coordinates of the points on the graph anymore because we can see clearly which fragments are above, on, or below the x-axis. So we will be looking only for that. In our inequality, Since the blue is supposed to be greater than green, we're looking where the blue graph is above the x-axis. So from that point of intersection, which we already know is at 4/3, the blue graph is above the x-axis right there. And therefore, the x solution set will go from 4/3, again excluding that endpoint, to positive infinite. Now, our inequality was of the form greater than 0, which means above the x-axis. So we were looking at the part of the graph of the left-hand side that is above the x-axis and identifying the corresponding x interval. We can have three other types of an inequality with 0 isolated on the right-hand side. Greater than or equal to 0, which will mean on or above the x-axis and its corresponding x interval. Less than 0, which will mean below the x-axis and its corresponding x interval. And finally, less than or equal to 0, which means on or below the x-axis and its corresponding x interval. Note that in our example, after isolating 0 on one side of the inequality, the other side was just a linear type of expression. So we were looking at the graph of a linear function. That means a line. We call such type of inequality a linear inequality. Now we will switch our attention to quadratic inequalities. That means inequalities in which, after isolating 0 on one side of the inequality, the other side will be a quadratic expression. We know that the graph of every quadratic function is a parabola, and we also know how that parabola can be aligned with respect to the x-axis from our discussion about the discriminant. Let's review a part of that. There were 6 cases depending on the sign of the leading coefficient and also the sign of the discriminant. A positive leading coefficient meant that the parabola will open up, and negative leading coefficient meant that the parabola will open down. If the discriminant was positive, there were 2 x-intercepts. If the discriminant was 0, there was only 1 x-intercept. And if the discriminant was less than 0, there were no x-intercepts. For all of those 6 alignments, we need to consider 4 different types of inequalities to identify their corresponding solution sets. So let's rearrange our table and copy the 6 alignments for all different types of inequalities. Let's first consider the inequality f of x greater than or equal to 0. To remind you, that means that the graph, the blue parabola in our case, must be above or on the x-axis. Let's identify these parts of the parabolas in all of our 6 alignments. I added the labels for the x-intercepts where needed. Note that in the second and third case, the whole parabola is on or above the x-axis. In the fifth case, there is only one point for which the parabola is on the x-axis, and in the last case, no part of the parabola is on or above the x-axis. Next, we recall that at the end we're looking for the x-intervals on which the parabola is where we wanted it to be with respect to the x-axis. So let's identify those x-intervals for each of the 6 alignments. The first case has 2 such intervals. In cases 2 and 3, the parabola is above or on the x-axis for all x's. In the fifth case, there is only one point for which we have what we need, and in the sixth one, there is no such x at all. Finally, we write our solution sets for each case in interval notation. In case 1, we have the union of two disjoint intervals with the endpoints included. In cases 2 and 3, we have all real numbers. In case 4, we have just one interval in the middle with the endpoints included. In case 5, there is only one point in the solution set. And case 6 has no solutions at all, so we denote it as the empty set. In similar way, following the same steps, we can find the solution sets for all the remaining types of inequalities for all 6 alignments. Note that if we have the inequality of the type only greater or only less than 0, none of the endpoints will be included in the solution sets, so we will have open intervals or unions of open intervals. It is also interesting to acknowledge that among the types of the solution sets that we're getting that haven't showed up in the first row, we have these two where all real numbers except just one number are in the solution set. And finally, a very important thing. You don't need to know and memorize these 24 cases. You will always simply go through the steps. First, isolate 0 on one side of the inequality, then graph the parabola from the other side, only minding the placement with respect to the x-axis and whether it opens up or down. Identify the parts of the parabola that are where they're supposed to be, above, on, or below the x-axis, depending on the type of the inequality. Identify your x interval, and that will give you your solution set.